Welcome. In this video, we're going to discuss an introduction to modular arithmetic. So modular arithmetic is all about taking integers and dividing them and finding the remainder. In fact, modular arithmetic is really just a study of remainders. Let's start with dividing an integer. Let's say you have an integer a and you divide it by d, and as a result, you get a quotient, plus you get some leftover part, a remainder of the amount that you divided by. So this could be something like 25 divided by 7. So if we divided 25 by 7, we'd have 3 for the quotient, 3 groups, and then there would be 4 leftovers of the groups of 7 that we divided by. Now, when we're working in modular arithmetic, we're only working with this remainder, this r here. So the key is that r is an integer. When we're doing modular arithmetic, we don't have fractions. There's no divide by d. There's no 1/4 of a remainder. There's no fraction of a remainder, no percent of a remainder. So what you can think of is taking this equation that we just wrote down and multiplying both sides by d. So the result of doing that gives us a on the left-hand side equal to d, what we divided by, and q, the quotient, how many groups of d do we have, plus just r, the remainder. So that's the equation that we're working with, and that's exactly where we start with the definition of what a remainder is and what a quotient is. So when a is divided by a positive integer d, the remainder is the smallest non-negative number. So a non-negative number could be 0, 1, 2, 3, or anything up to the mod, whatever you're dividing by. And that equation that we just proved is sitting right there. Notice that all of these numbers, a, d, r, q, they are all integers. Okay, so let's try to actually find some remainders just using a traditional method of long division. So how many times does 7 go into 160? 7 goes into 16 twice, or 20 times if you like. So 7 times 2 is 14. And then we'll take 160 and subtract away 140, and it leaves us with 20 leftovers. And 7 goes into 20 twice. And again, we'd subtract 14. And now we're left with a remainder of 6. So my r value here is equal to 6. Okay, now remember that we can also have negative integers divided by integers and figure out the remainder. Any integer is fine to divide by except for 0. So in the next problem, we're asked to do the same thing, but to decide what about negative 160 being divided by 7. So what we discovered above is that if we take the number 160 and we divide it by 7, we get 22 groups of 7 plus a leftover of 6. So what if we were to do the same thing, but with negative 160? So I'm going to take that equation and multiply both sides by negative 1, or just a negative sign. So you notice that we had to do a negative multiplied to all of both sides. So we really did need these brackets here. Okay, so what we would get out of that equation implies that minus 160 is equal to minus 22 times 7 minus 6. Now, unfortunately, this didn't quite directly tell us what we want. It's not okay to have a negative remainder. When you divide a number, you're always getting a positive leftover amount. Remember, if we scroll back above, the R number is always supposed to be non-negative. So we can't say, oh, here's my remainder, it's -6. So what we can do is add 7 and subtract 7 to what we've written here. So 7 added in and 7 subtracted. So what we can get as a result is -160 is the same as 1 less 7, so -23 sevens, and then 7 minus 6 is 1. So our remainder in this case is 1. So also notice that the answer of 1 and 6 add to 7, the mod that we got, which is what's going to happen when you take 160 and divide by 7, or -160 and divide by 7. And if you did this with different numbers, you would still have that property of these two remainders adding up to whatever the mod is, whatever we divided by. Okay, so as a further tool, we'll also discuss finding the remainder with the basic calculator. So we don't really want to use a calculator to solve all of these problems. The calculator does have limitations, namely that it's only going to deal with numbers of a certain size. Once you get beyond 8 digits, most basic calculators won't be able to give you an accurate answer for what the remainder is, at least by these steps below. So what we're about to talk about could be a good tool to check some of your answers or to make some of your own problems up to do by hand. So some quick steps to discuss. There's 3 of them. First, take the numbers that you want and divide them. Then subtract away the decimal part. So this part gets subtracted away, and just leave yourself with the stuff left over after the decimal point punched into your calculator. Now take that leftover stuff and multiply it by whatever you divided by. In this case, we divided by 7, and it will give me an answer of something like this. Notice that this number is not an integer. It's supposed to be an integer. We're searching for a remainder. Remainders are always non-negative integers. But what's happened with my calculator is it has a bit of a round off error. So it rounded off and it didn't quite perfectly keep all of the digits when you divided by, because it only stores so many digits in my basic calculator. So what we have to do is round it to the closest integer. But you should get something that is pretty darn close to your actual answer. So here my actual answer is 3. So I'll let you try this on your own just to find some remainder. You can use these steps above to try. Pause the video now and divide 1, 2, 3, 4, 5, 6, 7 by 7. So here's what I got. I divided by 7. I got a leftover part of 0.714. I multiplied that by 7 and I got something pretty darn close to 5. So 5 was my remainder. Okay, so here's another activity to just help you find remainders. You can try to do it by hand, or you can use a calculator if you really want to. So this will give us some good practice. Reading through the problem, it says choose any prime number. So we have to remember back to what prime numbers are. 2, 3, 5, 7, 11, 13, and so on. So any one you like other than 2 or 3, so it has to be 5 or bigger. Then we're going to find the square of that prime number. So let's say P is our prime number, and the first thing we're going to do is find the square of that number. Then we're going to add 16. So there's our 16. And then finally, we'll find the remainder when the result is divided by 12. So I'm going to play a little game with you right now. I'm going to try to predict the remainder that you get, even though I don't know which prime number you are picking. So we'll pause the video now. Go ahead and try to pick your prime number, find the remainder when you divide by 12, and I'll see if I can predict your answer. Okay, so did you get an answer of 5? The remainder should always be 5. So to give you a little bit of an explanation why, any prime number other than 2 or 3 has a special form. It's either a multiple of 6 plus 1 or a multiple of 6 minus 1. So if you take that number and you square it and you add 16, you will be able to write out that number as 12 multiplied by some integer plus 5. I'll leave it as a challenge if you want to try that on your own. Okay, now we're ready to introduce the formal language of modular arithmetic. So, two integers are said to be congruent. So we use the word congruent instead of equal in modular arithmetic. So they're congruent in mod M if both A and B have the same remainder when you divide by the mod. So the M value, the mod, is always what we're dividing by. And we're going to write that these two numbers are congruent when they have the same remainder. So in mathematical notation, we can write A is congruent to B mod M. So we'll identify the following as true or false. So in the following problems, what we want to do is divide and find the remainder. So if we divide by 10 and find the remainder, for 97 we get 7, and dividing 27 by 7 we also get 7. So the remainders are the same, so this one is true. In the next problem we have a mod 5, so we divide both sides by 5 and produce the remainder. So 29 divided by 5 has a remainder of 4, and 44 divided by 5 has a remainder of 4 as well. So those ones are also true. So we take 33 and we divide by 20, we get a remainder of 13, and the same with 93 divided by 20 also has a remainder of 13. So that one is true as well. 14 divided by 9 gives you a remainder of 5. So this one is false. It's false that 14 is congruent to 4 in mod 9. In the next problem, we have minus 4 congruent to 17 in mod 5. So one helpful tool that I really like to use, especially when you have negative numbers or maybe bigger numbers, is to think about multiples of the mod. So one thing I like to think about here is to add 5 to minus 4, because adding or subtracting the mod will not change the remainder. We'll continue to discuss that in the future. So if we add 5, I get 1. And on the other side, you could also think of that one of subtracting 15 instead of dividing and finding the remainder. It's another way to find the remainder, to add or subtract a multiple of the mod to get yourself down to the remainder. So here we get 2 left over, so this one is also false. The remainders are not the same. In the last problem, how about we do something similar? Let's try to think of a multiple of 9 that's close to 82. So how about 81? On the left, I can add 81, and on the right, I can subtract 81. So that gives me minus 1 on the left and positive 1 on the right. These are not the same in mod 9. Okay, let's look at some more examples. So here we have some bigger numbers to deal with. So remember, for mod 7, 11, and 13, when you're dividing by 7, 11, and 13, we can break things up into groups of threes. We can break the digits up into groups of 3. So let's go ahead and do that right away to remind ourselves that each grouping of 3 digits can be separated in all of these problems below. The same style of trick works for multiples of 7, 11, and 13. So in each of the problems below, we're going to view it in that way. So we have 1, 2, 3, 1, 2, 3. Remember, we alternately add and subtract these groups of 3. So plus and minus. And on the other side, we would get 3, 2, 1, 3, 2, 1, and alternately add and subtract these groups. And notice that you get 0 in both of these scenarios. So these numbers are multiples of 7, and they both have a remainder of 0. So this congruence is true. In the next problem, we have 1, 1, 1 and 1, 1, 1 as our two groups of size 3. And we alternately add and subtract those groups. We get 0 on the right-hand side. So the number on the right-hand side is a multiple of 11. And 44 is also a multiple of 11. So they also give us a remainder of 0 on both sides. Let's try the mod 13 example. So this time our groups of 3 are 0, 1, 1. So I'm just going to write 11 for that. And 0, 2, 2. So that's 22. And the last group of 3 is not a complete group, but that's no problem. You can still write 2, 2 for the last group of 3 on the left. And we alternately add and then subtract and then add the final one. So this time we get 11 on the left-hand side. So our remainder is actually 11 for this number on the left. Notice my usage of a congruent symbol when I'm saying that the remainder is 11, and below I'm just using a regular equal symbol to say that these numbers add and subtract up to 11. So let's do the same thing on the right-hand side. So on the right-hand side, we have 1, 1, 1, 2, 2, 2, 1, 1, 1, and we alternately add and subtract these groups. So out of this, we get 0. So this time the remainders are not the same. We have a remainder of 11, and we have a remainder of 0 on the right-hand side. So this one is false. Okay, so next we're going to dip into mod 3 and mod 9. So the rule for mod 3 and 9 was to add up all of the digits. If the result of adding up all the digits is a multiple of 9, that original number is also a multiple of 9, and the same works for 3. So in our first problem, we have 1, 2, 3, 4, 5. Those are all the digits that are on the left-hand side. So if we add up all of these digits, we get 15. And if we add up the digits in a different order, we're of course still going to get 15. Addition is commutative. So both numbers have their digits adding up to 15, so both of these numbers will have the same remainder. In particular, the remainder is 0 because 15 is a multiple of 3. So this one is true. For mod 9 below, we'll do the same trick. We're just thinking about dividing by 9 and finding the remainder instead. So 1, 2, 3 added together on the left, and then 3 plus 3 plus 3 on the right-hand side. So on the left we get 6, and on the right we get 9, and 6 and 9 will give you different remainders in mod 9. So the original numbers also give you different remainders in mod 9. So this one is false. I want to wrap up this video with a little bit of an introduction to the next video. We're going to make some heavy usage of the idea that in every mod, m is congruent to 0. So this is going to be a true statement, and I would like to prove to you why it's true, or at least give you some insight into why it's true. So if we take, let's say, mod 5. Let's say we take 5. What is 5 congruent to in mod 5? Well, you could subtract 5 and you get 0. So that's one way to think about getting 0. Or you could just divide by 5 and you have no leftovers. So it's 0 as well. The same would work for 6. 6 is 0 in mod 6. So if you take the mod and you just subtract away the mod, you always get 0. So this pattern continues on and on and on for every single mod. And this tells us why adding and subtracting the mod doesn't change the congruence. It keeps the number congruent to exactly what it was before. So a very helpful tool is to add and subtract the mod, because it's just like adding and subtracting 0.